In this video, we'll be talking about the gravitational potential energy, but in vast distances. So we're not using MGH anymore. We're using your derived formula from the universal law of gravitation. So this is the universal law of gravitation divided by r squared. R stands for the distance. So if you take the integral of force with respect to distance, you should get energy, correct? Normally you'd get work in this case. But in this case, since the force is only from the force of gravity, you'd get gravitational potential energy taking this integral. So if I take the integral of the universal law of gravitation with respect to distance, we can factor out the constants in this case from the integral, and we get left off with 1 over r squared with respect to r. The integral of this is equal to negative g m1 m2 over r. And this is equal to your gravitational potential energy over vast distances. Well, maybe you've noticed this, but what if you plug in infinity into here? Well, if you plug in infinite distance, you've completely escaped the pull of gravity. So technically, even if you're a trillion meters away, maybe a quintillion, 10 to the power of, I don't know, 100 meters away, you're still going to get some finite number. You're not going to get 0. Right? No matter how large a number is, the property of a fraction is not going to allow you to get 0 unless the denominator is equal to infinity. So you're never going to escape the force of gravity of something. Gravity is an infinite range. But if you're infinitely far, well, you've infinitely gotten away from the planet. Therefore, you've completely escaped the gravity. And when you treat distance as infinity, you get a gravitational potential energy of 0. So the closer you are to something, and the further you are from something, so let's compare these two. So the closer you are to something, r will be a lower number. It will be a smaller number in magnitude. Therefore, if you're dividing this entire thing by a smaller number, then you're going to get a larger number in magnitude. And if you're dividing this entire thing by a large number, a large distance, you'll get a smaller negative number in magnitude. So what I mean by magnitude is -5, even though it's a number less than -3. -5 has a larger magnitude of number, has a larger magnitude due to the fact of its the integer value or the absolute value of this number. It creates a larger magnitude, so it's, I guess, technically a bigger number, but not a larger number. Okay, you get what I mean. So how do you calculate escape velocity? So escape velocity. Well, in order to calculate escape velocity, you need to know that you need enough kinetic energy to get out of the pull of the gravitational energy. So gravitational potential energy it's kind of pulling you down in a sense. Not really, but kinetic energy is kind of the thing that's, I guess, resisting against the gravitational potential energy. So you need enough kinetic energy to go against your gravitational potential energy. Therefore, kinetic energy minus gravitational energy should be 0. Now, how do you set up this equation? Well, your kinetic energy is equal to the mass of, let's say little m, the mass of something trying to escape, times velocity squared, is equal to, actually, minus gravitational potential energy. Minus gravitational potential energy. This is gravitational potential energy formula. And all this should be equal to 0. Now, I wrote big M and little m to differentiate two objects. Big M is the mass of the planet, and little m is the mass of something that's trying to escape, like maybe a space station. So we can move both these equations on different sides of an equation to set them equal to each other. Therefore, your kinetic energy must be equal to the magnitude of your gravitational potential energy in order to escape. So we can do a little bit of algebra, cancel out the masses of the planet, multiply by 2, and then square root on both sides. And then you should get a escape velocity formula that looks like the square root of 2 times gm over r. So this right here is your escape velocity formula. And you can actually use this formula to solve some problems. Let's go ahead and work on some problems right now. So for this problem, you likely needed to derive the equation for escape velocity if I didn't already do it at the beginning of the video. Now, some formula sheets may have escape velocity in some classes and some might not, because this is not too hard of a derivation. I know my class did, so maybe your class does as well. But let's find the escape velocity of a projectile. So we notice that the mass of the projectile is not given because it doesn't matter in this equation. Only the mass of the planet matters. And it's a projectile on the surface of Mars. So I gave you the mass of Mars and the radius of Mars. The radius of Mars you can treat as the distance from the projectile and your center of Mars, because you're on the surface. So let's plug in all the things. So its escape velocity is 2 times the gravitational constant times the mass of the planet, 6.39 times 10 to the 23, over your distance. So your distance is your distance from the surface to the center of mass of the Mars, which is just the radius. So 3.3895 times 10 to the power of 6. And once you evaluated this, you should get a escape velocity of 5,014, approximately 5,015 meters per second. And as you can tell, you have to go pretty damn fast to escape the pole of Mars. So this problem is 100%, maybe not 100%, well, very likely, how about that, going to be on an exam of yours or a quiz. Because I had a problem like this twice on a quiz and an exam. So that's a double whammy for me. But a similar problem related to this was on both an exam and a quiz for me. So I'm going to show you how to solve for this. So in this problem, just read it first. So now if you read it, you need to know that you need to solve for the speed before it hits your atmosphere. And it says that you may ignore the size of the asteroid. Okay, well, how do you ignore the size of the asteroid? Well, we need to calculate kinetic energy. We need to use your gravitational potential energy formula, right? How do you ignore the mass of the asteroid? Well, it turns out that it actually cancels out. But let's set up your equation. So we're going to have to do some equation setting up here. Your delta K is equal to the negative of your change in gravitational potential energy. The reason why it's negative here is because we're using this formula for gravitational potential energy. If it was just a standard like ball on a hill type stuff, then your change in kinetic energy is equal to your change in gravitational potential energy if it was just ball on a hill. But since we're talking in large scales, your change in kinetic energy is equal to the negative of your change in your gravitational potential energy. So if we set this up fully, and now if we keep expanding this, change in kinetic energy is equal to negative final kinetic energy minus initial kinetic energy. And your change in gravitational potential energy is, well, final gravitational potential energy minus initial. So we can actually, well, substitute in your formulas for kinetic energy and gravitational potential energy here. mv squared. So the kinetic energy we're talking about is the kinetic energy of the asteroid. So we'll represent the mass of Earth with big M, and the mass of the asteroid with little m. Asteroid. Now we can write down all of these. mvf squared minus 1/2 mvi squared is equal to the negative of your final potential energy. So negative g big M over M divided by your distance minus your initial gravitational potential energy, so which can be written as plus instead. G big M little m r. So it's your total derived formula. And what we can actually do is isolate v of f here. But before that, well, turns out we can actually cancel out mass in each one of these terms. So each of these terms has, in this equation, has little m in here, the mass of the asteroid. That's why we can just ignore it. So if we rewrite this equation as 1/2 vf squared minus 1/2 vi squared is equal to, and let's distribute the negative here, is equal to positive g big M. Sorry, this is final distance and this is initial distance. G M R final minus G, oh, I wrote the big M, RF minus G big M RI. So no little m. That was canceled out. And I distributed the negative along this problem here. So how do we isolate v of f? Well, we're going to have to clear some space for that. Okay. Actually, I could just make this smaller. I don't want to remove this because you guys might need this for your steps. So let's make this smaller instead. There we go. Now it looks better. So how do we isolate v of f? Well, let's move all the terms on one side. So we can write down 1/2. Let's move all the terms without v of f on one side. 1/2 g m. Can we do that? Gm. We can factor out Gm 1 over 1 minus r of f minus 1 r of I plus 1/2 v squared, vi squared, more specifically. So if we multiply 2 on both sides, you get v of f squared is equal to 2 times gm 1 over rf minus 1 over ri plus vi squared. So multiplying 2 on both sides cancel out the half here. And all we need to do is square root all of this. So if we square root everything, you should get the final equation of 2gm 1 over final distance minus 1 over initial distance plus initial velocity squared. Now, this is where the radius of the Earth comes in. Let's actually clear out all the work here. This is the derive formula. This is where the radius of the Earth comes in. So, when the asteroid strikes the surface of the Earth, it's at a distance, r of f, of the radius of the Earth away from the center of mass of the Earth. So the asteroid doesn't strike straight to the center of the Earth, right? It's still going to have some gravitational potential energy due to the fact that it only hits the surface. That's why we have a final distance here. So let's go ahead and plug in all these numbers. So let me explain all the values here. This 2 is just your constant in this equation. This is the gravitational constant. This is the mass of Earth. So big M, we didn't cancel that out. This is the final distance, and the final distance from the asteroid, or the meteor now that it's in Earth's atmosphere, the final distance, r of f, is the radius of Earth since it only strikes the surface. And this is the initial distance. So the initial distance was 5 times 10 to the power of 7 kilometers away, but I turned this to 5 times 10 to the power of 10 meters away. So I changed the unit from kilometers to meters, and I got 5 times 10 to the power of 10 instead now. And in the initial velocity, v of I squared, this is v of I, is just 2 kilometers per second, but I turn this into meters per second. So 2 kilometers per second is equal to 2,000 meters per second. Now, once you plug in all these numbers, and hopefully you don't make any mistakes at this point typing all this into your calculator because you've gotten so far already, but once you find or plug everything into your calculator, you should get the final answer of 11,353 meters per second, which is insanely fast. Now, the mass of the asteroid is going to decrease as it enters the Earth's atmosphere because it's just going to it's going to get set on fire. It's just going to ignite, and parts of it's going to break off, you know. So in real life, it's not actually going to be this fast. It's probably going to be slower due to air resistance and the size of the asteroid getting smaller. But this is an approximation with perfect conditions. So as always, I need to mention OpenStax. Link will be down in the description. It's an online textbook, and I get my problems from there. So the 2 problems I did in this video, I got from there. So if you want more practice problems, OpenStax is great for that. Link will be down in the description. Now, if you think what I said in this video helped, then consider subscribing and liking the video. But as always, if you have any questions, put it down in the comment section.